They understand that. We want to somehow capture the electron. How do we do that? All right, the way we do that is we need to make a separate cell, or you might think of the cell as a container.
Yeah, like a cup.
Yeah, for each half reaction. All right.
By the way, can I just tell you for a second, we're kind of lying to you. These aren't actually separate half reaction cells. These are actually two separate batteries in here.
Yeah,
but we'll explain that later.
All right, now here I have a particular system where, for example, I've got copper sulfate in one cell or one container, a beaker of some kind. And on the other side, I have zinc sulfate. I have a piece of copper. It's hard to see here. There's a piece of copper and also a piece of zinc. And this will make, and this galvanometer is like a voltmeter. It measures how many volts pass through it. All right. Now there's something missing though. There's a problem with this particular cell. Mr. Siemens, what is that problem?
Well, it looks like we're missing the salt bridge.
So you need something called a salt bridge. And what happens for that is that this allows the ions to move through your cells. So you need to kind of make a note of this.
Electrons are negatively charged. If we just let the electrons move through, we'd get this real big buildup of negatives in one side.
It kills the
cell. And things in nature don't like to be polarized like that. They like to be balanced. Right. So to do that, we're going to have to relieve the negativeness of one of those cells.
So here's the actual picture if you look down here. Here's the salt bridge so that the ions can flow. So if you put a salt
lime in the coconut. Oh, sorry.
The cell will produce voltage or electricity for a long time.
Put the lime
in the coconut. Okay. Now another way that you can do this, the picture we have, sometimes the salt bridges can look a little bit different. You could actually have the salt bridge.
The porous disc salt bridge.
Yeah, it's a different kind. It's actually easy to draw, frankly. You could have one right here, and then right through here we have something called, those little things are called a porous, P-O-R?
O-U-S, I think.
O-U-S, disc.
Yep. It's just a chunk of ceramic.
A little piece of ceramic that's right here at either end, and then we can have the ions that can flow right here, and then you would still have what we call an electrode, typically a piece of metal, and then between that you could put a you could put a light bulb, frankly, and it should light the light bulb up, and you could then, now we have made a battery. So a battery is simply two containers, two beakers or whatever, and these are typically aqueous solutions, and then you've got a couple of metals, and it works.
Yeah.
It's pretty cool,
Two half reactions of a redox.
Yeah. And you'll have one half reaction take place on this side, and the other half reaction takes place on this side. Typically, it involves the particular metal that you've immersed into the solution.
Yep. Typically, but not always. We'll talk about that.
So now what we want to do is we want to label all the parts of a galvanic cell. All right. So let's actually draw another picture. You're going to find yourself drawing tons of these pictures. All right. So let's take the classic picture. The classic galvanic cell actually came from a guy by the name of Galvani, of all things. Imagine that. Yeah. Whew. We planned that. And you take these little rectangles are pieces of metal. Let's say that this piece of metal is called copper, and this one is zinc. And typically we would then put into this solution some zinc nitrate. Let's say Zn2 positive and NO3 negative. And on this side, I'd put some, say, copper nitrate, copper 2 nitrate. Could be sulfate, wouldn't matter, no difference. Now, what am I missing?
Salt bridge.
Got to have that salt
And you got to
bridge.
have a wire connecting to your metals, too.
All right, so let's make that kind of a liquid solution here. And then we'll have a salt bridge. This, by the way, is a filled, and it's called a YouTube, actually.
A YouTube?
Because it's in the form of a U, upside down.
But not like YouTube.
Not like U2.
No, or YouTube.
YouTube. Oh, I got it. Oh, yeah.
He's old. It takes him a while.
Yeah, I'm an old man. And then you need a connection, and we'll just put a V here for the voltmeter. All right? All right, so there's our picture. Okay? So we have our picture. Oops. We have our picture here. Looks like the colors went away, Mr. Sams. All right. Oh well. And so we have this is a battery. Now I want to label the parts. Now before we do this, we have to realize what are the half reactions that are taking place. Now as we're doing, actually, let's come back to this because we need to talk about electrical potential. I think.
Yes, we do.
Don't we?
Yeah, we do.
All right,
which
so,
one's the anode and which one's the cathode.
And actually, we have this picture. We'll come back to that picture. So save that for just a moment, ladies and gents.
Coming back.
And there is sometimes what happens when one of the electrodes is not a metal. okay, you have some problems like that. Let's say you're producing a gas. Some of them do produce gases. What you do is you would have a piece of platinum. You would still use a metal. The platinum doesn't actually react, but it gets immersed into the solution. And this is like an inverted test tube right here on this particular side. And then you can have the gases present, and then the reaction still takes place on a piece of metal. You still have to have essentially a piece of metal immersed into the liquid. But you can do this by having gases present. So this particular reaction is hydrogen, and the hydrogen is going through the solution, and then you can get bubbles coming out and stuff like that. And so that's what you do when you have one of those.
Yep. And by the way, when we talk about the electrical potentials here in a little bit, you're going to see some of them are positive, some of them are negative. Those numbers are pluses or minuses relative to the hydrogen electrode that you see right here. Hydrogen in the electrode is kind of the zero. Everything else is based off of that. And that's how we get those numbers.
So let's take a look at the table. So when we go to the table, this is actually your handout. So this is a very important table. The table is standard reduction potential table that you can see right here. And you can see some values. For example, lithium is negative 3.0. Here's one for lead. And something that's very intriguing about this particular table, we haven't sort of told you this before, I'm sorry. You've always been trying to balance all these half reactions, haven't you? And you know what? Did you know there was a table with all the half reactions in it? Yay. And you didn't have to actually balance them. If you could just find the right half reaction. Oh! So there you go. We were lying. So for example, if you want the 10 one right here, I just want this to go away. Okay, if I want the 10, it keeps coming back. Why does it do that? Bizarro. So if I want the 10 one right here, there's the reaction, and there's these numbers, the 0.15, and you know, here's a whole bunch more. It's kind of a busy table. And so this is just your handout, right, guys?
Yep.
It's got lots of different things. And so what we want to do is we want to go back to that one, and we want to look at the different values for the zinc and the copper.
Yep, I saw both of those on the first page.
You saw them both on the first page. Yep. Very good.
So zinc is right here.
Here's zinc. So and we're going to round probably 2 digits, I think. So here's the zinc one right here. So zinc positive 2. So let's go back to that. So let's go back to this screen, this picture right here. So we have Zn positive 2 plus 2 electrons goes to zinc. And the number for that was
negative
0.76 volts. Now we got that off the table.
Yep.
Now we can also have the copper plus 2 electrons. That goes to the copper. And if you look on that table, that is positive 0.34 volts. Yeah, that's right. Okay. Now, what's the problem, Mr. Sams, with these reactions?
Well, they're both reduction. We need one to be reduction and one to be oxidation.
So what do you think we need to have? How would I decide who needs to reduce and who needs to oxidize?
Well, ultimately, you need your voltages to be positive, because if you have a positive voltage, it's a spontaneous reaction. We'll talk about why later.
So what we need to do is we need to flip the top reaction around.
Yep.
So what I'm going to do is right down here is I'm going to write Zn goes to Zn plus 2 electrons. And on this one, I'm going to leave the copper plus 2 electrons goes to copper.
Right.
And if you add these two voltages, that'll be positive 0.76 when you flip it. If you flip it, you multiply by negative 1.
Yep.
And this will be positive 0.34 volts. And this is 1.10 volts. So the voltage, if you had a voltmeter set up in this particular system, it would read 1.1 volts.
Hey, I wonder if that's what this would read if I had it hooked up on my little clock.
I believe so. Yeah. Now let's talk about some more things that are happening in this cell. Now in all galvanic cells, or batteries if you will, there is a positive and a negative side.
Yes, there is.
Yeah, like a battery. You look at a battery, it's got a positive end and a negative end. So we actually give names to those positives and negatives. They're called what?
Anode and cathode.
The anodes and the cathodes. And anodes, oxidation occurs. Guys, you should write this down somewhere.
Yes.
A blank screen here. We'll skip this. Oxidation at the anode.
Anox.
And reduction, D-U-C-T-I-O-N. Reduction is at the cathode.
Red cat. Red cat, anox.
Is that how you do it?
Yeah, red cat.
Do you guys always remember? You know, an A and an O are both
vowels.
Vowels.
My
An
son
R
was a-
and a C, they're both
Consonants.
Keep your vowels together. Keep your consonants together. That's how I remember it.
I like red cats.
Okay, it works for you too. All right, so